Okay, so
the door's locked in 126.
It is 132 already?
133 is full.
Okay.
He's full at 36.
Okay.
Hey, Tom, I need your help submit.
26 doesn't know how to start the system. I asked him to go and look for help from Charles.
Okay.
Okay, time to start the class. I received multiple emails asking about alternative sections of this class. And there is a section that meets in this room Monday, Wednesday, Friday at 1 o'clock, from 1 o'clock to 1:50. And usually they're available empty seats in the main lecture hall here. And there is another section of the same class on Tuesdays and Thursdays from 4 o'clock to 5:15, again in this room, and again, there are available seats in the lecture hall. So if you want to attend in person, you have those options. Feel free to do it. I'm going to post the recordings that I have so far on WebAssign website, just for simplicity, rather than handling multiple websites. WebAssign should be the only one, and it will be simpler for everybody. Okay. About units in physics, we said that we were going to use the SI system of units, and the basic units for SI system of units were kilogram, meter, second. You have candela for light intensity. You have Kelvin for temperature. You have mole for about for amount of material that has atomic and molecular structure, and that's pretty much it. You have for angles, you have radian, and one important unit that we need is part of the basic system of units is ampere. So this is the basic unit. This is the unit that we need for electricity and magnetism. So we shouldn't forget that one. So those are the 7 basic units. And the claim that I made last time was that everything in nature can be expressed quantitatively using only those basic units, or a subset of those basic units, surprisingly. Very often, those units are either too large or too small to be convenient for practical applications. In cases like this, the SI system of units has a set of prefixes that provide a fraction or multiple of 10 of the basic units. What does this mean? For example, the unit for length is meter. in SI units. However, if you want to describe, if you want to express the distance between Pocatello and Idaho Falls, instead of, well, you can say it is about 50,000 meters, but it is more convenient to say that it is 50 kilometers. So the prefix kilo is assigned in front of the name of the unit to express 1,000, 10 to the power 3 of meters. Similarly, if you want to express the size, the average size of the coronavirus, for example, again, the meter is not the most convenient unit to do that. Instead, you can use micrometers, and the prefix micro is 1 millionth, 10 to the meter. So most of the prefixes that you're going to encounter in this class and in many other classes are listed here in this list and in your textbook also. And the most often used prefixes are marked with red, and it's a good thing to know those without asking about them. It is part of any science class that you take. You don't probably need to write them down, or, but they should be familiar to everybody. Okay. Often you have data expressed in alternative units. Instead of using SI units, very often you can hear temperature measured in Fahrenheit, energy measured in British thermal units, length measured in feet or miles. So in cases like that, you may need to convert from one set of units to the set of units that is conventional in science, the SI system of units. And the textbook gives you a simple procedure to do this conversion. So there are many ways to do this conversion. If you have your own favorite conversion method, please use it, just do it correctly. I'm going to give one simple example of conversion of units from miles per hour into meters per second. So let's say that you're driving to Idaho Falls, and at some point your speed is 85 miles per hour. And of course you get a ticket and all the other fun stuff. But let's convert this from miles per hour into normal SI system of units, meters per second. To do conversions, you always need external information. You always need a conversion factor. In this case, you need two conversion factors. The conversion factors are always provided to you, or you can read them from a table or from Google or from other source. In this case, the conversion from miles into meters. The conversion factor is this. 1 mile is approximately 1,650 meters. So this is the first conversion factor that we need. You also need a conversion factor for hours into seconds, because hours are not part of the SI system of units. So 1 hour is how many seconds? 1 hour is 60 minutes. Each minute is 60 seconds. So you have 60 times 60, 3,600 seconds. Now take your speed, v equals 25 miles per hour, and multiply that speed by unity, by the number 1, dimensionless unit number 1. But your dimensionless unit number 1, you take the following form of this number 1. You say, you take this expression and say that 1650
Work.
1 mile.
The only,
Yes,
so you might have to leave the lights on, just because the owl has like really, you want to use the video, it's really hard for it to use.
is this better or how? Okay, so what is this ratio? Well, if you take this equation and divide both sides of this equation to 1 mile, this equation is exactly 1. Unitless number, dimensionless unitless number. So your factor of 1 here, you can write it like 1650 meters divided by 1 mile. And you do formal type of cancellation of miles with miles, and you end up with 85 multiplied by 1650. And since the miles canceled out, the units that are left are meters divided by hour. In other words, 85 miles per hour in reality is this number, 85 times 1650 meters per hour. After that, repeat the same procedure once more, multiply by the unitless number 1, but now take the unitless number 1 from the second conversion equation. So you have here hours in denominator. You want this conversion to cancel hours. In other words, you want hour here in this equation to be in nominator. In other words, you want your unitless number 1 this way. 1 hour divided by 3,600 seconds is my unitless number 1. Put that unitless number 1 right here. So 1 hour divided by 3,600 seconds. And again, you have formal cancellation of the hours, and the units that are left are, you have 85 multiplied by 1650. So use your calculator, do the multiplication and division. The answer is going to be something close to 44 meters per second. In other words, conversion into 85 miles per hour is 44 meters per second. Notice something simple, but you have to stick to it. When you do a midterm exam or anything, and you do some calculations, and you end up with a number. After that number, almost always you have to have appropriate units. Very rarely, the number that you get is unitless. So when you're doing a midterm test, make sure that after the number you enter, you have the units, otherwise the grader is going to be unhappy with your answer. Okay, remarks and questions so far? Okay, the next part of chapter 1 is something again very simple, something that we call dimensionless dimensional analysis. So it is a very simple procedure which you can use to see if certain mathematical result is meaningless. And the procedure is like this. Let's say that you do some calculations like we're going to do next week, and you end up at the end with a formula which says the velocity of an object squared is equal to 2 times the acceleration of that object multiplied by the displacement x of that object. The question is, can we make a simple reasoning and see if this result is wrong? What I mean is the units on the left-hand side of this expression have to be the same as the units on the right-hand side. So the units for speed, as we said, is meters per second. So on the left-hand side, you have meters per second. And since the speed is squared, the units on the left are meters squared divided by seconds squared. While on the right, the number 2 is unitless. So it doesn't have dimension. The acceleration, as we're going to see, has units of meter per second squared. And distance, displacement, has units of meters. Therefore, this particular equation is dimensionally correct. It doesn't mean that this equation, this particular equation, is accurate, but it could be correct. For example, if instead of a factor of 2, here you had a factor of 3.7, this equation also is dimensionally correct, but you're going to see that it is not accurate. So this simple dimensional analysis that we just did, you can apply it in many cases, in many practical cases, to see if you didn't make a mistake somewhere in your problem solving. Okay, and actually dimensional analysis is something as simple as it is. You can do cutting edge research just using simple dimensional analysis. Let me give you the following example. In physics, you have one fundamental number called fine structure constant. So the fine structure constant is a constant of nature which describes the strength of electromagnetic interactions. And that constant, it is denoted with alpha, is defined as elementary charge squared divided by 4 pi epsilon naught h bar c. Here in this equation, E is the value of the elementary electric charge. 4 pi are dimensionless numbers. Epsilon naught is electric permittivity of vacuum. We're going to deal with it next semester. H bar is Planck's constant, measured in joules times seconds, and c is the speed of light. So this combination of numbers occurs regularly when you're trying to describe any electromagnetic phenomenon. So it has its own name, fine structure constant. Well, what are the units for this fine structure constant? Well, you can go and unravel and substitute the units for each of those variables. For example, the electric charge is measured in ampere times second. Similarly, H bar is measured in joule times second time, and so on and so on. When you do this substitution, you're going to end up with the result which says that this particular combination of variables doesn't have dimension. It is dimensionless number. Its value is 1 divided by 137 approximately. It looks like combination of constants of nature that gives you a dimensionless expression has some particular deep, interesting meaning in science. So if you're so inclined, you can write a simple computer program to find a wide class of dimensionless expressions using only constants like elementary charge, Planck's constant, speed of light. You can, with a simple computer program, you can find a wide number of those expressions and see if those expressions have any physical meaning, like the fine structure constant, for example. Well, by the fine structure constant, this dimensionless entity has this particular numerical value. Nobody knows so far. But people have played around with numbers, and somebody noticed that this number is pretty much very accurately given with the following simple numerical expression. 2 to the power negative 4 multiplied by 3 to the power 2 multiplied by pi to the power negative 1/4 and multiplied by 5 factorial to the power negative 1/4. So why a constant of nature that we just can measure, why that constant of nature has this particular simple numerical representation? Nobody knows, but this is an interesting question that you can think about in your spare time. Any remarks and questions so far? Yes.
I heard that the people in the Zoom chat, Blackboard is really blurry.
We cannot do much.
I can't do much. I've got it.
Is there some dust on the owl on top?
I don't think so. I think the issue is that the whiteboard or the blackboard itself is fairly dirty.
Oh,
So in the future, I'm gonna try cleaning the whiteboard between
oh
classes.
my goodness.
I don't.
What a mess.
Yeah.
This morning, there was an announcement that several other universities in different parts of the country went completely online. And I am afraid that we may end up with the same situation. But for the moment, we just have to do as good as we can. We don't have other options. So keep in mind that, well, let's continue with the material and not talk about things that will not change.
Dr. Tatar,
But
yeah, I'm just gonna write down what you have on the board on our board in here too, so people can see it if they're in this room.
Thank you. I'm not going to erase anymore, but okay. So the next section of chapter 1 is a simple, short introduction to trigonometry, let's say. So Some of you had some trigonometry in the other classes. Some of you had a trigonometry course here at ISU. But you don't need too much, too detailed knowledge of trigonometry in order to use it. So in your textbook, you have a short definition with a few questions to check the understanding. And you probably don't need anything more than just this definition, but make sure that you can apply that definition in multiple aspects. So the simplest way to define trigonometric functions is by using right triangles. So consider the following right triangle. So here is one right triangle. The right angle, let's say, is here. And let's say that the lengths of the sides of the triangle are length A, length B, and the hypotenuse of the triangle has length C, let's say. Let's say that the angle opposite to the side A, this angle opposite to the side A, is angle alpha. By definition, sine of that angle, sine of angle alpha, by definition, is the ratio of the length of the side opposite to the angle, this is side A, divided by the length of the hypotenuse. It is just a definition. So it can be shown that this ratio cannot be a number larger than 1. Why? Because in any right triangle, the hypotenuse is the largest, the longest side in any right triangle. So some number divided by a larger number is always smaller than 1. Okay. In a similar manner, you define cosine of that angle alpha. So you define it as the ratio of the side adjacent to the angle, here, side B, divided by the length of the hypotenuse again. And two more trigonometric functions that we're going to use. Tangent of that angle, alpha, is defined as the ratio of opposite to the angle side divided by the adjacent to the angle side. In this case, it is A divided by B. And occasionally, we can use cotangent of the angle alpha as the ratio of adjacent to the angle side divided by the opposite to the angle side. So it is B divided by A, which means that the cotangent is the inverse of the tangent of the angle alpha. And it also means that, well, the tangent, okay, the cotangent is going to be also cosine of the angle divided by sine of the angle. Similarly, the tangent, I probably had to say that, the tangent in a similar manner is the ratio of the sine of the angle divided by the cosine of the angle. It is a lot of, too many definitions, but what we're going to use mostly are sine, cosine, and tangent. And very often, we're going to not use the definition in the way it is written here, but very often, for example, we're going to express this definition the following way. We can say the length of the side A is equal to the hypotenuse multiplied by the sine of the angle alpha. So we're not going to write the definition that way, but we can do it this way. Or we can do it by saying the length of the hypotenuse is equal to the side A divided by the sine of the angle. So it will be a little bit of a learning curve when we start solving triangles, analyzing forces or displacements, but eventually you're going to get used to it because eventually it is something quite simple. In many cases, you're going to have problems where you may want to calculate the value of some angle. In cases like this, you're going to need the inverse trigonometric functions. So what does this mean? This means the following thing. Let's say that here, this definition, I want to figure out which angle has sine with this numerical value. Okay, let's do it this way. Let's say that you're told that certain angle alpha has sine equal to 0.5, let's say. And the question that you may want to answer, or the problem may want to you to answer, which angle has this particular sine? Which angle has the value of the sine equal to 0.5? In that case, you say the angle alpha that has this particular value is the inverse sine, or it is called arc sine of 0.5. So arc sine is expression of the inverse function, inverse to the sine function. And if you plug in to your calculator, well, the calculators are a tricky thing. So the correct notation for inverse sine is arc sine. But it is in your calculators, the button that calculates the inverse sine is denoted with sine -1. Notation that is used on the key, on the appropriate key of the calculator. Confusing mathematically because we're not talking, this is not equal to sine of 0.5 to power -1. It is not that. It is, this notation just means arc sine. And if your calculator is adjusted in degree, the answer that your calculator is going to give is what? Go ahead. 30 degree, yeah. So of course you don't need to memorize that inverse sine of 0.5 is 30, because your calculator knows that already. In a similar manner, you can use inverse cosine. So for example, if you're told that cosine of certain angle beta is, well, what number should we use? Okay, let's do again 1/2, 0.5. And you're asked which angle beta has cosine of 0.5. And the answer is given in terms of inverse cosine or arc cosine. So you say the angle beta is obtained by applying the inverse cosine function to the number 0.5. Then your calculator prefers to use cosine to -1, which is again confusing. And if you plug in this, what angle are you going to get in degree? 60 degree, and so on. In a similar manner, you define the inverse tangent. So those are preliminary mathematical concepts. People that have had mathematical classes in math recently are probably going to feel comfortable with them. If you have forgotten this material, it will take a little bit of refreshing of your knowledge, and the textbook, together with the appendices to the textbook, are going to help. And of course, I'm also available for help. Remarks? Okay. The next topic is important. And again, if you have forgotten geometry, it could be something counterintuitive. It is a short discussion of the concept of a vector. So, in science, quantities may be completely described with a single number. For example, the temperature in this room, or in this, the temperature in this part of the room right here, it is, let's say, 300 Kelvin. A single number gives you a full description of the value of temperature at certain position. Other entities need more additional information to be fully described. For example, if somebody asks you, where is Idaho Falls City Hall located? Well, you can say it is a distance of about 51 miles from here, but in which direction? The number 51 doesn't give you a complete description of the location of Idaho Falls City Hall. In addition to the number 51, you need direction. In other words, a number, numerical value, a quantity, plus direction. This system of information we call vector. So in science in general, vectors are denoted with an arrow. The length of the arrow represents the distance, in this case, the distance to Idaho Falls City. And the direction given with the arrow gives you the direction of the vector. Notationally, you can use either small or capital letters. For example, this could be vector A. So to keep in mind that A is a vector quantity, we use a vector notation on top of the letter. So in our case, here is the description of the position of Idaho Falls City Hall, this vector. The length of the vector only the length, only this 51 miles length, is denoted either this way with absolute value, or the notation that I prefer is just the letter without a vector sign on top of it. So this denotes the length of the vector, or the magnitude, we call it magnitude of the vector. And in our case, this is, let's say, 51 miles. You can convert it to meters if you want, but this is standard notation for vectors. Now, what is going to be the tricky part of this section is to define and keep in mind the rules for addition of two vectors, subtraction of two vectors. Because those rules are a little bit not intuitive. Let's say that you have a vector A, and let's say that you have another vector, vector B, like this one. How do you define the sum of those two vectors? Well, the sum of those two vectors is defined as a vector that is constructed using the following rule. You take vector B and you draw the vector B starting from the head of vector A. So here it is. You keep the same direction and magnitude as vector B. So often actually in science, we work with so-called free vectors. Free vector means that you have the right to take this vector and move it to any place you want. Just make sure that you keep the magnitude and direction unchanged. So this and this vector are representative of the same class of vectors that we call free vector V. So you have the freedom to do this movement of vectors. So by definition, the sum of vector A plus vector B is a vector C that is constructed by connecting the tail of the first vector to the head of the vector, the last vector, the vector that you're adding. So this vector, call it vector C, it is by definition equal to the sum of A plus B. So why do you need some weird, unusual way of addition? Well, you want to keep the properties of a sum similar to the property of a sum of ordinary numbers. This is the simplest possible definition of summation of vectors. You can convince yourself that the sum of two vectors is commutative. In other words, A plus B is the same thing as B plus A. You can convince yourself, you can introduce a vector in opposite direction and so on. Associative rule. So the usual rules that numbers satisfy are going to be satisfied by this definition for vector summation. Okay, let's say that the magnitude of vector A is 5 meters or whatever, let's say meters. Let's say that the magnitude of vector B is what? 2 meters. What is the magnitude of vector C?
7.
Well, it would be nice if the magnitude of vector C was 7. And it could be, actually. But in general, the magnitude of vector C could be any number between 7 and 3 meters. 3 meters. It could be any of those numbers, depending upon the mutual orientations of vector A and B. So let's say if A and B were pointing in the same direction, the magnitude of the sum would have been 5 plus 2, 7. If they were pointing exactly in opposite direction, the magnitude of the result would be 5 minus 2, 3. And if the direction of A and B is something between the same and opposite, it will be some number between 3 and 10. Okay. This reasoning about magnitudes is usually a source of trick questions in exams, MCAT exams, physics midterm final exams. So entity is a simple concept, just keep it in mind. Don't get caught in, and you have, in the first homework assignment, you have questions related with this magnitude of the sum. Now, how do you subtract two vectors? How do you subtract two vectors? Well, again, there is a rule, geometrical rule, again, counterintuitive, but you have to know how to do it. If A plus B is this vector, let's construct the vector that is equal to the difference of A and B. So let's construct a vector that is A minus B. And the rule is this. Take a representative of vector A, after that, draw a representative of vector B, starting from the tail of the first vector. So this is representative of vector B. By definition, the difference of the two vectors, the vector A minus B, is a vector constructed by connecting the heads of the two vectors. So this is vector B equal to A minus B. Direction of the difference should be in direction of the vector from which you subtract. You subtract from A, so the direction has to be the way it is here on the board. Again, you can demonstrate that some of the usual rules that are valid for numbers are valid for vectors. Keep in mind that A minus B is different from B minus A as vectors. Just like numbers, right? 8 minus 2, 6. But 2 minus 8 is not 6, but negative 6. So B minus A actually is B minus A actually the opposite of vector B. So it is a vector just like B, but in opposite direction. Again, you can demonstrate that the magnitude of the difference of two vectors is a number between the sum of the magnitudes and the difference of the magnitudes, like this. For our case, D is a number between 7 and 2, 7 meters and 2 meters. Four minutes. So next time I'm going to tell you how to add and subtract vectors using components. But you need to know the two methods for addition and subtraction. The geometrical method that I just presented, and you also can use the coordinates, which is actually quite simple. But in many cases, you do not have the option to use coordinates, so this is why you need to know the two ways to do the vector addition and subtraction. And what is also left from this chapter, after we deal with vectors, is a little bit of applications of geometry. And as an application, I can use some of the examples that I have in my notes. Or alternatively, you can put some problem from the textbook or from the homework assignment on the board, and I'm going to solve it as an example of how to use vectors, add them, subtract them, and so on. So you have that option. Please sanitize the seat for the next class, and also use the door on the back as an exit, and people that are closest to the door should exit first, just for safety of everybody. If you have questions about any part of the material, including the homework, please talk with me in class, out of class, via Zoom.
Situation right now. What can you do, you know?
Yeah, well, we appreciate your extra effort. Yes, thank you.
You know what? So here there is a question about if you already have a paper copy of the textbook, you don't want to buy the ebook. So I talked with this company that runs WebAssign, and they say, oh no, we cannot decouple them. You have to get the ebook no matter if you need it or not. Very unpleasant experience, but this is how they have the power at this moment. We cannot do much.
Okay.
I tried to decouple the ebook from access to the system, but it's not successful. We don't have much leverage.
Thank you. Quick question, will you use the same textbook next?
Yes, next semester we have to use the same book. We don't want to keep buying different things.
Like when you go to buy it.
But next year, students that are going to take this class next year, I'm definitely going to change the textbook because this price is not acceptable. They're just extorting us that this is what they're doing.
There is an option to buy it cheaper for 2 semesters or even one.
Yes, if you're planning to take the second semester, go that way.
Are you teaching classes? Because I was looking at the schedule last semester, so I was trying to figure out my spring semester for the next semester.